Hey Will, what are we going to do for lab 4?
That's a great question. How about we go shoot something? Go shooting. It'll be really fun.
Yeah, let's go shooting.
Let's go shooting.
I have a buddy who's got a really cool 6.5 Creedmoor with a suppressor on it. He's got a spotting scope with a camera on it so we can tell when we hit stuff. We got lots of other cameras. We got a chronograph so we can tell how fast the bullet moves. We should be able to come up with something with that.
All right.
Sounds good.
Sounds boring. Wait a minute. But we need to know exactly when the bullet will hit the target.
I got you covered on that one. My wife had this great idea to announce the gender of our baby. You get 2 pounds of tannerite, like 12 pounds of chalk, and when you shoot it, it goes boom.
I like booms.
Okay, so we measured that the muzzle velocity is 2,650 feet per second, and then it's going to shoot down range toward the target with a vapor cone, a mock cone, following the bullet. And so, kind of cheating and using ballistics charts, we know that the trajectory of the bullet and the velocity of the bullet is actually a kind of a parabolic decay, but it's really, really close to linear because we're on just a tiny part of the parabola. So this is actually really inaccurate, and if we just map it up from 1,200 feet, this is really close to the velocity that the ballistics charts say. So we're going to use this information to kind of start our calculations.
So to find the drag coefficient, we went to figure 9.24 in the book. We found the coefficient of drag, and using the Mach number that it was traveling, we found that the average coefficient would be about 0.45.
So now that we actually have our drag coefficient, or the average drag coefficient over the ranges that we're predicting for our bullet, we can go through and calculate what the drag should be, and from that get our final velocity, knowing our initial velocity. So drag is just mass times acceleration. We know what our drag is equal to in terms of our drag coefficient, and through the derivation we can come to this equation for our final velocity. The only thing we need now is an actual time, so let's go shooting.
So we start with our first test at 100 yards. The bullet is in the air for about 0.1 seconds, and yes, it is a boy.
Oh, it's a girl!
For the second test, we backed out to 250 yards. This time, the bullet is in the air for 0.3 seconds. And I must say, Greg looks pretty pleased with the shot. For the final shot, we backed out to 400 yards. At this range, the bullet travels for just over half a second. We shot at 2 cans, hit both, but we're not able to get either to ignite. Notice in these slow motion shots that you can see what is called a vapor cone or mock cone trailing the bullet as it travels to the can.
Okay, so this is our final breakdown of all our results after shooting and running through the calculation that we had made. Taking our times that we pulled from the video at each of our 3 distances, 100, 250, and 400 yards, as well as calculating with no drag, so like our physics 121, drag's not a factor, incompressible flow, which has been this class, and compressible flow, which has been kind of what we're experimenting with. We calculated what our final velocities should be. So we start off with 2650 across the board is what it should have been without flow. It's your physics 121. For incompressible flow, you can see that we were above 2,200 feet per second. The reason why that's interesting is tannerite has to have a velocity, impact velocity of 2,200 feet per second, Mach 2-ish, in order to ignite. So according to this, if we hadn't taken compressible flow into account, it should have ignited. But we saw from the video that it didn't. So if we take compressible flow into account, right when we get up to 400 yards, so above at 100 yards and 250 yards, we're still right around that Mach 2 number, and we obviously got it to ignite. The second we get out to 400, we drop below that Mach 2, and so according to our math, it shouldn't have ignited, which it didn't. The thing that's coolest, though, is if we take our ballistics calculator, which we use as our background of what we should be experiencing, our ballistics calculator says at 1,200 yards, we should have had about 1,950 feet per second, which is almost exactly the same as what we calculate.